Okay, welcome back, everyone. We'll continue with the next talk by Mr. Bönicke from Newcastle University, and we'll speak about dynamical asymptotic dimension equations.
Thanks, Ulrich, for the introduction, and thanks to the organizers. Been here for 3 weeks as well, and it's been a very nice time, very productive. So yeah, I want to give you a bit of an overview about this notion of dynamic asymptotic dimension. So I'll start with a sort of big picture overview of why we might be interested in this, and I'll tell you what it's good for. And in the end, I'll tell you a couple of computational techniques, how can we actually estimate this dimension. So I'll start with a completely novel idea. So start with a groupoid, and then we can build a seesaw. So it's something you've never heard of before. Right, and then we'll often over here, we're then interested in understanding the structure of our seesaw algebra that we're interested in. Maybe we're interested in ideals and so on. Maybe we're interested in whether it fits into the classification program. And then we might also be interested in its invariance, for example, K-theory, trace space, and so on and so forth. And we've got similar questions over here, of course. So here we have, starting maybe with invariance, we have homology, and we have other things that are interesting from a groupoid perspective. Here's this idea of topological full groups. And there's a nice interplay between all of these ideas. And key to understanding many of these things is actually understanding the structure of the groupoids first, because the structure of the groupoids often tells us nice things about the structure here. And once we understand the structure of any object, it might usually also help us answer the other types of questions better. So I want to really focus on the structure here. So what's the easiest kind of groupoid that we can think of and understand its structure? Or maybe not the easiest one, but a particularly simple class. So suppose H is an ample, compact, and principal groupoid. Okay, so it's totally disconnected. There's no fixed points. Principal says, and we see it's compact. Well, that H has a very simple structure. Oh, by the way, I'll only talk about locally compact Hausdorff groupoids on this talk, so I'll not always write that. That's sort of an assumption in the background. Well, in that case, H has a very simple structure. Namely, it will just be some subspaces of my unit space times the full equivalence relation on finitely many points. And we've got maybe finitely many copies of this. So we can decompose our groupoid very nicely. So this guy is just 1 up to ni squared, full equivalence relation of units of groupoid. So this is very nice, this is something we can understand very easily, and this is just the disjointed of such very frequently understood things. And if we go to the seesaw algebra, it just means, well, that we've got some continuous functions on C0x with values in the appropriate matrix algebra, and then a direct sum of those. So it's a very easily understood seesaw algebra. We can do a bit something slightly more general, maybe going beyond the ample case. We really use totally disconnected here in a nice way to get us a proper decomposition of the base space. So if I'm already giving up. So now assume that G is étale and H is an open subgroupoid of G and relatively compact. Then we cannot necessarily do this nice decomposition because, first of all, the base space is no longer totally disconnected, so we cannot decompose the base space nicely. Also, our groupoid is no longer compact itself, so it's a bit harder to talk about the quotient. as a nice space. But it turns out that the groupoid is still very nicely behaved, so it behaves very similar to this guy. In particular, the C saliva H is still subhomogeneous. And that's because basically what my relative compactness condition tells me that my orbits are uniformly bounded still. And then I can do a bit of representation theory to show that this is still a subhomogeneous and so on. Okay, so these are sort of the easy groupoids that we can understand quite well. And then the general philosophy, maybe, to understand groupoids, more general groupoids, might be for general G, approximated.
Please mute. Yeah.
Yeah. I tested this one, it seemed to be the best one. Okay. We'll try this one. Let's see how long this one holds up. Maybe we should give these a name. Let's call H like this, or like this. Call such H elementary. So there's various notions of elementary in the literature. So this is just sort of a philosophical idea of being an easily understood groupoid. So this is not a technical definition of elementary now. It could be either this or this. But what we want to do is we want to approximate G by elementary. Elementary subgroupoids. And there's two ways around that people use. The first one would be to find a corner sequence of elementary H in G. So this is what leads to the idea of almost finiteness. This is Tui, and then also if developed to further, this leads to the idea of almost finiteness. Right, so we basically ask that for any large compact subset in our groupoid, there exists an H which is K epsilon further inside the groupoid in an appropriate sense. So that's the notion I don't want to talk about. So we've heard a lot about that already in the first week. And the other one I want to talk about, maybe I'll switch to blue, is that better? Likely. It's in the how I want to say this, so just how to phrase. So I want to uniformly decompose orbits of my groupoid into orbits of these elementary orbits. I and count how many you need. That is the idea of dynamic asymptotic definition. Okay, so that is what I want to focus on for the remainder of the talk. So let me now give you the definition again. So it's been on the board already in Kristen's talk, but let me write it down again. Here maybe. So this is due to Günther, Willett and Yu in a 2017 paper. So an entire groupoid G, globally compact also, has dynamic asymptotic dimension at most d. If the following holds, if for every K in G open and relatively compact, let's actually assume, let's maybe assume that the unit space is compact to make things a little bit easier. Then we can assume that our K always contains a unit space. So if for every such large open relatively compact subset of G, there exists an open cover U0 up to D of G naught, such that if I look at the groupoid generated by elements in K, whose source and range is in fixed UI. So this is my notation for the restriction of the groupoid to that subspace. I'm only looking at arrows starting and ending in the same UI. And that is relatively compact. So it's one of my elementary things, right? I'm saying the dimension is D if I can approximate it by D plus 1 elementary things in this particular way. Okay, so let me try and draw a picture what this means. Okay, so we have our, in particular, why this is a sort of reasonable phrasing of what's going on here. So let's assume this is my UI, but this is sort of not the right way maybe to think about it, because the UI will not necessarily be a connected thing. So we should think about our UI consisting of several components here. So these are all part of UI. Okay, and then I'm starting with my K. So I have my little sigma in here, and the lag span, I don't know if that's a word, is that a word, lag span? The lag span of the sigma is, they can only go at most K, right? So when they start in here, at some point, they can walk around, you know, go to another point, go to another point, go to another point here. Maybe they can go back to the previous point. But what I'm saying is that these things here should be bigger than K apart. So whenever my guy starts in one part here, they cannot leave it. And the number of points they can reach here is uniformly finite, is uniformly bounded. That's what this essentially is telling me, the compactness of this thing. Right, so whenever I pick a point and look at my partial orbit, my K orbit, I'm only allowed to take steps in K and never leave UI. So this here, the rest of it, all of this here. This is a subset of X minus Y, and this is lava for this guy, right? So can't go there. So they're sort of stuck on their little island here, cannot go there because they would have to cross the lava. So they're stuck here, and here their orbit is finite. So here they can only do finite. That's the sort of picture in mind. Right. Okay, so now back to some slightly less informal things. But I want to give you some theorems first. Normally, I would give these kind of talks the other way around. So I would give you lots of examples of DAD, groupoids, and then I never get to the actual results in the end. So trying to turn things around. I want to tell you about what this thing is useful for first, before we can then think about some examples and how to compute this. First one is what we've already seen the questions talk as well. So this is, well, I don't remember all the years of the Atlas paper. So the G et al. Principle second countable groupoid, then the nuclear dimension of the reduced C-star algebra of G is bounded by the dynamic asymptotic dimension of G and the dimension covering dimension of the base space G naught. Okay, I actually didn't write so DAD, but like short and notice for dynamic asymptotic dimension. And we need little plus ones everywhere because it is a multiplicative formula, so to make sure that one of these things is zero, not everything collapses on the right hand side. Okay, and then Courtney Bönicke gets to Hoof and Saviola extended this recently to the twisted case. So if now sigma over G is a twist, then you can add that here and the formula stays the same. Nothing changes otherwise. And then recently with Han Li, we sort of tried to figure out exactly when twisted groupoid C-star algebras are subhomogeneous. And that allowed us then to basically remove the principal bit here. So small improvement. And then there's more work by Dana Bönicke and Astrid, where they deal with certain classes of groupoids that have bigger isotropy. So I should say, so having finite dynamic asymptotic dimension still puts a big barrier on the isotropy you can have. So in particular, every isotropy group has to be locally finite. So that just follows straightforward from the fact that these groupoids here need to be compact, relatively compact. So removing the principal here really just gives you sort of, you know, if you've got sort of finite fixed group or something flying around, then we can now deal with that. But yeah, Dana and Astrid have something for bigger isotropy groups by basically the idea that if the isotropy groups vary continuously, then you can mod out that bundle of isotropy groups and still get a result that looks very much like this. So there's some ways to go beyond this obstruction of only having finite or locally finite fixed groups. Right, so another theorem where DAD has popped up is work of Li, Liao, and Binter on who introduced this notion of diagonal dimension, and they showed that the diagonal dimension of G is a lower bound. The dynamic asymptotic dimension of G is a lower bound for the diagonal dimension of the inclusion of C of G naught. So in particular, G needs to be principal because we want C of G naught to be a diagonal in C star G. And in that case, the DAD makes perfect sense and has a chance to be finite. So we get a lower bound in this way, and quite often, quite well, sometimes, maybe I say sometimes, sometimes people, so for example, when the unit space is totally disconnected and the groupoid is a transformation groupoid, then you get quality But I guess it's expected that this equality holds slightly beyond the class of transformation points. Right, so that's one thing on the structure side, and then one nice, I think, advantage maybe of this dynamic asymptotic dimension over the notion of almost finiteness is that it somehow keeps track of a little bit finer information, right? We have this dimension. And that can be used in other ways. So here's a theorem I proved with Clément de la Guerra and Bailey and Rufus Willett, which says that if G is ample principal sigma component, then the homology groups of G, which also appeared in all these lectures in the first week quite prominently, they all vanish in degrees above the dimension. Right, so this dimension also picks up some finer information on this side. Nice, and in the top degree, we get a Jordan free group too. So in particular, we have the following nice little corollary, which tells us that if so this is using the spectral sequence developed by Rieti and Yamashita. Theta plus all results from above. Is that we can actually compute in low dimensional cases a K theory just from the homology. So if, for example, if that G is at most 2, and we know that H2G is finitely generated, then A0 the starting one. It's just H0 of G, direct sum H2 of G, and A1 the H1 of G. And so this result of creating Yamashita tells us that there's a sort of general spectral sequence which has the homology groups on the E2 page and converges to K theory CR star G under certain nice assumptions, which we certainly have when G is at most 2 and principal. That needs to go there. Yeah, so if the dimension is at most 2, that means most of these homology groups vanish, then the spectral sequence collapses quite quickly, and you actually just get a short exact sequence where you can write K0 as an extension of H0 and H2. We know that H2 is origin free, then also finitely generated must be free, so that admits a splitting. So we get direct sum decomposition here, and here we get a nice morphism directly. So you can say some nice things on the homology side and K theory side as well for this notion of dynamic asymptotic dimension. All right, that is sort of the results I wanted to show you where this can be used. And now in the last 15 minutes, is it? I'll tell you a little bit about what we know about the values of this thing. So can we actually show that this thing is finite in some cases? So maybe Yeah. Okay, so examples of computing the dimension. So already in the original paper with evolution, you made a couple of nice observations and proved a couple of nice theorems about this. So the first thing, which is not very hard to see from the definition, is that the dimension is, what do you definition is here, is 0. Well, that means I don't need to pick anything here. I can just take the whole unit space. So basically it just says that the through point generated by an open relatively compact subset generates a group, relatively compact through point itself. So this thing happens if and only if my G can be written as a union, directed union of such things. Say G, a directed union of open relatively compact subgroup points.
How close is that to being AF?
Well, I guess in the AF, for these AF group points, you typically ask for principal. Here we don't ask for principal, so we allow a little bit of torsion, I guess. But well, I mean, there's a
principal and arm that somewhere.
I think that should be same as AF. Then yeah. Correct me if I'm wrong. Is it not? No, maybe you have a nice paper where you compare all these different notions that are flying around it. AF. Maybe we can have a discussion afterwards about what exactly. Right. So the next one, suppose we have a minimal action where my group gamma is a virtually cyclic group and X is just any constant Hausdorff space. Then the dynamic asymptotic dimension of the associated transformation group is always 1. So they don't need things over here. So in particular, if we take the Z action, that is or that's dimension 1, or if we take an action of the infinite dihedral group that we get prominently in Wilhelm's talk yesterday, those things will have dimension. More generally, if X is compact Hausdorff and gamma is say ZD, and ZD acts on X. Really, the dimension of X is finite, then the dat of the transformation groupoid in this case just D. So in particular, what you can see quite quickly is that well, this notion doesn't really seem to depend very much on the dimension of X, right? So it really just seems to pick up the action of the dimension of the acting group. So the phase space dimension seems to be completely irrelevant, at least in these experiments. And then finally, something that's not a transformation groupoid, XD is a discrete metric space. bounded geometry, then you can build, or Candalis, you tell us how to build what's known as the coarse groupoid. So that's a groupoid encoding the large scale structure, the coarse geometric structure of X. And that coincides precisely with the classical asymptotic dimension of the space in the sense of Gromov. And this is really, I think, what this notion was modeled after. So it was really modeled to make this result work. And then this is the definition that came out of it. It seemed to still give nice results that we have seen on the other side of the uniform row algebra. And it seems to go through for more general groupoids using this dimension, which is quite nice. Okay, and then the final couple of minutes I want to mention some permanence properties. Here again. We've got some actual examples. Of course, the next thing you want to ask is what kind of permanence property it has. And here's a theorem here summarizing some of these results. I got is that if G and H are Rita equivalent, it's a very natural question to ask. Does that leave the dimension invariant? And indeed it does. So then the f of G is equal to the H. Second thing, if I can cover my unit space, if I can open cover of my unit space by some open subsets U, I can compute the dat of those. And I'm telling you that that G is just the maximum of the dat of all the restrictions to open subsets in my finite cover. And so U, curly U, and finite cover of G naught. Well, this is kind of, I mean, the dimension of the restriction is smaller than this one. It's not so hard to see. But here, what really happens is, I mean, you might have arrows that go from one U to another U. So what this tells you is that you can actually ignore all those arrows going from one U to another one. You can just restrict. So that is the difficult part in proving that theorem, that you can sort of throw away a bunch of arrows and still get the same dimension. The dimension of a product is bounded by the sum of the dimensions. So again, you just look at the definition, quite easy to get some upper bound, a multiplicative upper bound, right? You just take the U's for your copy of G, you take some V's for the copy of H, you just take all possible products, so Ui, Vj, that will form a cover of the product of the unit spaces, and will give you a nice upper bound on the dimension here. Doesn't work. So the content here is really bringing it down to the sum, which is a bit more tricky. And finally, well, it should have really been maybe the first one because it's maybe the easiest of these. If G is a nested union, open subgroupoids, then the G is at most the limit of the individual dimensions And in the last 5 minutes, I can give you one brief example, stringing some of these things together. Now, over here. Example. So we've seen a lot of examples coming from global actions. So an actual question might be, okay, what about things that are not global in nature? I mean, that's why we study group choice in the first place, right? To have some sort of local dynamics. So what about partial actions? So suppose I've got a zero-dimensional space, and I've got a partial homeomorphism, so homeomorphism between two open subsets of X. So this is a homeomorphism, and U and V are both open subsets of X. So that generates a partial action of the integers. Right? Assume that the associated transformation group void for this partial action is free. So then, of course, we would immediately maybe say, okay, that would probably have dimension 1 as well, right? But working with partial actions is much harder somehow verifying this directly. But you can now string together a nice couple of observations. So Shirley Geffin observed that we can write this thing as an increasing union of partial actions theta k, theta n, maybe n, yeah. Theta n, such that each of these guys is now supported on a Clopen set, so it's generated by something on the Clopen set. So we can actually globalize it. So such that theta k is globalizable, which means that there exists some other space yk and a global action and alpha k from that yk such that this action is just a restriction. So yk, x is contained in yk, and I obtain my original guy by just restricting to this subset x sitting inside yk, or y, sorry. I'm mixing n's and putting some, sorry. Yn. So in particular, what this means is that my partial product here is Morita equivalent to this global guy. And I'm doing the same thing again, and I shouldn't change conventions. I want to use this on the fly. Right, and now we're basically done, right? So we can now just string together the first and the last part here. So we know that each global free action, so this action will also be free, and this space will still be zero-dimensional. That comes from the construction of the globalization. So this guy will have dimension 1. So this guy will have dimension 1 for every n. So by the inductive Ullmann result, this thing will have dimension 1 as well. So we get a nice result for these partial actions, which are generated by a single automorphism. So my original transformation group void as dimension 1 and more. Maybe that's a good point to stop. Thank you.
Any questions?
So when you then take this algebra for this part collection, whatever construction you use for that.
Yeah.
So that does it have nuclear dimension one? Exactly, or?
Well, yeah, it would, yeah, because it's typically
Okay,
not,
so
I mean,
nuclear
unless the
dimension
space,
of that space, that one then, or two. So
well, here I'm
so
assuming
what do you
that
know about
the,
cyst algebra?
here I'm assuming that the base space is zero dimensional in this result, so I've erased this thing, so yeah, it would, so it's at most one, and unless this space is sort of finite and you get sort of benefit, then you don't get any, that will be dimension one.
I wanted to ask you, the zero dimensional is what allows this observation by Giffen.
Sorry,
The observation by Giffen that you
Yeah.
can restrict to problem
mhm.
is because it is zero dimensional.
Yes, yeah, so that is essential in real work. I just found this very neat. I haven't actually tried to see if I can do anything more general, but that is certainly yeah, that's essential here, I think, in the way she proves it. Yeah, it would be interesting to see. I also don't know. One can do similar things for other actions. If this is a sort of general technique, I haven't tried doing that. One can always nicely decompose a partial action of a zero-dimensional space in this way into globalizable ones. So it would be nice to know, I guess.
So, if you have a, say, a principal group point and you, equip it with a length function,
Mhm.
separate all the fibers.
Yeah.
Then you get a nice extended metric space and you can compute its, say, asymptotic dimension.
Yeah.
Is that related with the
Yeah, it's actually, well, yeah, it's a result I didn't get to write down. Yeah, actually, it is, at least if G is ample and principal, and E naught is compact, then the AV of G, if I know a priori that the dimension is finite, then it must actually coincide with the asymptotic dimension of this extended metric space. Then,
and you need ample for this?
Well, possibly not. So for transformation groups, it's known that you can do finite dimensional spaces. But yeah, I mean, the sort of basic examples that we had on the board suggest that this should somehow hold very gently, right? Because for example,
Yes.
for these integer actions, we don't need any information about the space to get dimension one, to get to the optimal dimension. So yeah, this might be a lack of techniques somehow more than an actual obstruction.
So, back when you were mentioning the using that homology result to get some K-theory computations, when you have data greater than 2, can you still say something about the K-theory, or is it just messier than what
You
you?
can still say something. I mean, there's this general spectral sequence over that which takes in the homology groups with coefficients in the K theory of C0 G naught and converges to the K theory of the C side, reduced T side. So you can still say something, but you just have to understand the spectral sequence, right? So this is just the nicest to state result somehow when everything collapses. In general, you can still do something, but you have to understand then the differentials and what happens in the spectral sequence too.
Is that a variation of the arterial spectral sequence? Or is that
Yeah, it's Polish, it is. So yeah, I mean, the tools they use is sort of built on this Maya nest approach, it's ABC spectral sequence, and Maya has developed in quite some generality. But I guess the idea is for spectral sequence, I guess also fits somehow in that framework if one phrases it properly.
any further question? that's not the case, then it's the same.